Okay, hello everybody. So Stacy was saying, okay, I'm really excited to be chatting with you, and we're going to be talking about, it sounds like a very ambitious title, searching for life and habitability in our solar system. But I have to say, mostly has been heavily impacted, this specific theme, what we call astrobiology, by the recent functioning of the James Webb Space Telescope. So let's go about this. So this is a new era in James Webb. So James Webb started taking operations in June 2022. So let's say 1 year and a half ago. And already in all that time, we have pointed to many objects in the solar system, and we have released many discoveries. And just to give you a sense, this is our solar system. They are not to scale, but just to give you a flavor about the objects. So you have the main planets here, and then you have the different moons underneath. So you have an idea. I mean, there, of course, every planet has a lot of moons, but we also, the colors indicate the targets already being observed. The bluish colors or more darker colors indicate things that we already pointed James Webb to take observations and make science out of that. So we went to all the major planets, and we went to a lot of the moons, and we also went to comets, centaurs, asteroids, and in 1 year and a half already there has been a lot of science. So in this talk, I will try to kind of summarize or tell you what is happening, what are the new things we're learning from with this telescope, and what are the new frontiers. And if you've been following the news, you have seen some of these pictures in the media and some of the newspapers, because some of these images are beautiful. You can see the power of this new telescope, because the telescope has two main big important things. First, is huge, is a big telescope, and being so big allows you to get these very highly, very highly accurate and also very high resolution images of the objects. And the second big important thing is very, very cold. And being very cold is excellent for us when we do infrared astronomy, which is very difficult to do. For example, Hubble, when you think about Hubble, is a great telescope, which is smaller than James Webb, but it's great for optical astronomy, for take pictures that we can see with our own eyes. But for example, in the infrared, where there's a lot of information about the composition of the objects or their evolution, their history, and so on, you need the infrared. And this telescope has been designed to do that. So this telescope is taking a huge amount of pretty pictures, but also pulling out a lot of science out of these objects. And I mean, one of the things you can see, these beautiful rings, Neptune and Uranus, and then I will tell you more about the ocean wars, and of course Mars, the main belt, and Saturn. So I will be focusing mostly what we call relevant objects in the solar system, and I'm going to tell a bit about Mars and the ocean wars in this talk. So how do you search? Now, there's a big debate. How do you search for life on a different planet? And when we think about life, there's so much emphasis on Mars, not because it's just Mars and it's really close, which is one of the closest planets that we can go together with Venus. But I think one of the main things that drives Mars so interest is because it's actually very similar to our own planet. But when you take a picture, these are modern pictures of the two planets, and you can see they are very different. Our planet is, of course, full of life. We have an active hydrosphere, we have oceans, we have rainforests, we have cloud decks moving all around. And then you look at Mars, and it does look like a dead rock. I mean, you do see the polar caps. There are polar caps on Mars. They're mostly made of carbon dioxide ice. It will be dry ice on our own planet, but there is no completely different in that sense. Yet, if you take out all the water, I mean, if you actually take out all the water from our planet and you aggregate it in a little bubble, it will make that little bubble you can see there on our planet. So we are still a terrestrial planet. We're made of rock. Our planet is a big rock with this very thin layer of water. And that small layer of water, it makes a dramatic impact on what we consider life. So but the main message of this figure, and if you look at Mars, because Mars is colder, Mars cannot hold water in the liquid phase on the surface. It will always be in the vapor phase, or it will be only in solid. So it will be ice. It behaves like a dry ice in our planet, which is a dry ice in our planet is actually the ice of carbon dioxide. So the only way we think that there could be water, liquid water on Mars, is always below the surface. And this is our emphasis. And you can see below two numbers there. this is the way we quantify how much water a planet has. It's called GEL, or Global Equivalent Layer. So what does it mean? If our planet would be a sphere, our planet would have, almost 2 miles, let's say 1.5 miles of water, 2.7 kilometers of water, thick ocean covering the whole planet. And in the case of Mars, it has most of the water, again, in the polar caps underneath that CO2 ice. Together with the CO2 ice is water, and it will make a not an insignificant ocean of 30 meters that will cover the whole planet. So Mars has a lot of water. It just does not, doesn't have an hydrological cycle as active as our own planet. Yet, we did measurements using various telescopes, some from ground, some from actually orbiting Mars. This is work actually I've been leading them. That's most of my career has been focused on this. One of the things we found out is that on Mars, there was a big ocean in the past. Actually, when our planet life was being started in our own planet, there was a big ocean on Mars. And you can see that that ocean has been disappearing over time. It was localized in the northern part of the planet, and then over time has been lost. So Mars, being smaller than our own planet, the gravity holds things less. So water can easily escape, easier than our own planet. So that is the fate that Mars happens. So, but we think in the past, it might have been much more habitable than today. So when we think about Mars, we're thinking, where did it happen? Where did all that water go? And if there's any remnant of that ancient habitability hidden below the surface of Mars. So where we think could be habitable today on Mars, and we always look below the surface. So if you stratify the surface of Mars, there is a photic area, we call it. We call it photic because the photons are hidden there, and it's kind of an aggressive area of the planet's surface. It will try to break, DNA bonds, or classical molecules will be broken down. As you go deeper into the planet's subsurface, then you start getting ice formed, but it's still not liquid. And then if you go, people claim kilometers, some people even claim a few meters below the surface, you should be able to find liquid water on Mars. So a lot of the search for life and habitability on Mars is being focused on the subsurface. And that's one of the main features we want to do is we want to drill on Mars and try to go 2 meters deep. We're also looking for some facades or some areas that allow us to go below the surface without having to drill. So that's kind of the future frontiers when we think about Mars. So what type of life are we thinking about here? We're thinking about very simple life. If you have radioactive materials, you break bonds, you get hydrogen. That hydrogen is like food, together with carbon dioxide is, food for a little bacteria, and that bacteria produces a residue methane. So that is what we call a prototypical life we're thinking about. We're not thinking about a big animal or humanoid. We are thinking about very simple life, where archean life, bacterial life that may be active below the surface. We know all these ingredients are active on Mars. We know there's hydrogen. We know there's water. We know there's carbon dioxide. We know there is radioactive processes. So the only thing, to be detected here is the life. So one way to do that is to look for proxies, like in this case, this gas, methane, which is the natural gas you use for your kitchen. And the interesting thing is that we use in telescopes, we found that in 2009. And it was a very difficult measurement, and we spent many years working on this data. We also saw water associated with in some of the cases, but not always. But the interesting thing is we saw this natural gas coming out on Mars at specific locations, and then we only saw it at a specific time. And that was very surprising. There was one challenge with these measurements. We made these measurements using telescopes in our own planet. And when you look at a planet like Mars for our own planet, we had to go through our own atmosphere. So actually, we measure two things. We measure the methane in our own planet, which we do have a lot, and we do measure the methane on Mars. And we did our best to remove everything we knew about the methane on our own planet, but we are never sure if we remove it all perfectly. So there has been a lot of debate about the validity of these measurements because of the complexity in doing that. So we have sent an orbiter to Mars to see if we can actually detect this natural gas. And I will tell you a bit more about that. So the main Orion hypothesis that we are thinking about is below the surface of Mars, perhaps, this is an idea, we don't know yet, there is maybe an aquifer, and that aquifer may be blocked, or typically locked. Maybe there's biology or geology active there. And it may be connected by maybe a pore, by some ice, like blocking, like a cork blocking that place. And then by, the pressure may build up in this aquifer, and then that pore is a vent, and then you may release this natural gas. That's the Rhine hypothesis that we are imposing to see if it's there or not. And the challenge is that there could be multiple ways to get methane on Mars, and that's the challenge. So it's like in every science process, you can get methane on Mars by different ways. Mars could get hit by a comet, which is unlikely, but who knows? It could be meteorites, or of course, you could have geology below the surface acting with that rock and water, process called serpentinization, and then you release natural gas to the surface. And of course, the more interesting one, we can say, the hypothesis is that you may have some bacteria producing that gas. So that is the way you can make methane on Mars. And the interesting thing about this gas is that it should disappear pretty quickly on Mars, because the atmosphere will oxidize it and it will be gone, the molecule. So the moment you see this, it's like you're detecting something very recent that happened on Mars. So we sent an orbiter on Mars the mission is called ExoMars, actually still flying around Mars today. It's called ExoMars. It was being designed specifically to look for signatures of life, methane and other organic molecules. And we didn't see it. We searched everywhere. And I know this plot is a little bit busy, but what is this plot telling you is that in the x-axis is the latitude of Mars. We look at different latitudes of Mars, and in the y-axis is the altitude. We actually probe the atmosphere at different locations and at different places. And you see there's an X at the bottom. If you see it, maybe you see that close to zero, it says Gale Crater. Well, there is a rover there, Curiosity, who is actually making measurements of methane, and they do see methane on the surface of Mars. And unfortunately, because of the way the orbiter operates, we cannot make measurements together with Curiosity rover. So we have like a complementary view. The thing is that Curiosity occasionally see these plumes of methane, but we don't see them. And we search everywhere. So the debate about if the gas is there and where is more active, still active on Mars. And, just to tell you, these are very small amounts. We're not talking about a massive jet of huge amount of methane. We're talking about very small amounts. We're talking about parts per billion, which is, if you think about the atmosphere has billions of molecules, well, maybe one of them is methane. So we are using James Webb. And one of the first things we did when this telescope started to take data was to point to Mars and take data. And we did that, the operation started in June. By, I think, August or actually early September, the telescope was pointed quickly to start taking data of Mars. And we had the data. We've been working on data. The data is actually public. Actually, everybody can work on that data, but we still don't see methane. And we are working diligently to see, what's going on, if it's, how sensitive is there. And it makes a big impact on the possibility of something's happening below the surface of Mars. And just to show you, this is, my expertise is called spectroscopy, which is the characterization of light on the planets and, detecting how molecules interact. And just wanted to show you what we are looking for. This is what we call a spectrum of a planet. This is in the infrared. And, every molecule has a fingerprint, absorbs light at specific positions in specific colors. So what we're hoping to detect is something like the red feature. You see methane absorbs a light at a very specific color, and not all, it's a dominant color there. So you go to that place and see if there's a specific depression in the colors there, and that tells you the gas is there. That's the way we use to detect molecules in other planets. And that's the beauty of having telescopes. You can make that measurement from here on Earth or from space without having to be physically on the planet. So moving to the other cool objects in the solar system. So, if you ask me, this is all super biased from my side, but I have my own ranking of what I think are the most, astrobiology or interesting for searching for life and habitability. And I think the top three, for me at least, are Mars, Europa, which is the moon of Jupiter, and Enceladus, which is the moon of Saturn. And I'll be telling you about those three. Of course, there is a potential for maybe life also or an ancient life in Venus. Titan is, is rich in hydrocarbons, so it's another fascinating world in our solar system. But I think these two objects are very interesting, and I will tell you more about, especially start with Europa, which is closest. It's close, Jupiter is closer to us than Saturn and the moon Enceladus. So what do we know about this moon? So if you look at the moon today, it's actually a crust of ice. It doesn't look very appealing, but there are a lot of cracks. It means that ice is constantly being cracked and fractured, and it's being geologically new, we can call it. But the main thing that we know by the shape of the way the moon interacts with the Jupiter, it gets fractured all the time, and underneath that there is a big layer of we can call it subsurface ocean. Actually, we think there's some debate about if it's globally contiguous or more patchy, but in essence, there is a subsurface ocean underneath that big crust of ice. So imagine a place which has all this water, maybe some rock interior activity, but hydrothermal activity on the below the surface. So you have energy, you have water, you have a very confined, nice place. You may have organic compounds. That's the mixed search we want to see. And that may be releasing through those cracks into the atmosphere to see. And there has been some claims that those plumes are releasing material. So the main thing we wanted to do is with James Webb is to see how active Europa is. So one of the things we were assigned, actually we've been working in this program for 10, 15 years, is to go to Europa. This is what we can do. We can actually make a lot of measurements. We have like a grid. For every one of those, we call a spaxel, or that is those squares, we actually get all these colors, as I was showing you before, of all these molecules. So allow us to see, this is a model. This is something we were planning in 2016. And one of the things we can see is that this is the prediction that we were trying to test. That if those molecules, we're talking about carbon dioxide, carbon monoxide, ethane, methane, these are all hydrocarbons. This is the foundation for life as we know it. Water, of course, and we wanted to look for all those compounds and see if we can see plumes being released from the surface of Europa. That was the main objective of our James Webb data. And again, it was a big priority of this observatory. So again, they took data as fast as possible, and it was difficult because Europa is a small moon close to a massive bright planet. So organizing those observations took some time, but it did pay off. And this was actually published very recently, actually in October or September. We published this. This is an actual image we took with James Webb. And the image is great, but I think I will show you then, the main finding is not in this image, but it's in the spectrum of the colors of the moon at different places. But one of the things you can see clearly already in this image is that there is an area, white, and the other one is more bluish, different than the other ones. And that area is called the Tara region, is the name. And what is that area interesting for? But it's interesting because it's called a chaos terrain. It's a terrain that is already very, structurally different than other places. It's like, something being broken down. There's more fractures. The other ones look more flat, stable. That one looks like more something is being broken down and happening there. So when we went there, we took the data, we actually discovered for the first time that there was a carbon source in Europa. And that is, we actually discovered CO2 ice on the surface of the moon, only exposed at those locations, which is the terrain. And what is the relevance of that? Well, the big debate about Europa is that we are sure that there isn't water in the ocean, but we don't know how diverse chemically that place is. And we know life as we know it requires chemical diversity. It requires carbon, requires hydrogen, oxygen, and nitrogen, for example. So the fact that we know how water has hydrogen and oxygen, and now we have CO2. So now we have a carbon source, organic compounds require carbon. So that was a big discovery, and opens the idea that maybe below that crust of ice, maybe the conditions are maybe suitable for life, or maybe it gets more interesting. So then opens the idea. We were sending a mission called Europa Clipper now to explore Europa in detail now. And the main idea is now we know we're going to study this area. This is now a high priority target because now we will see if that CO2 gets really deposited all the time, if it's a plume actively being delivering material, it may provide a linkage or window into that subsurface ocean. So that was, just came out with James Webb a few months ago. And I think the other one, the other object, which I think is also is fascinating, is Enceladus. And it's very similar. It's also an ocean where the two are very, very similar in that sense. The Enceladus is a little bit smaller, but it has also a massive ocean underneath. And we were lucky with Enceladus is because we had a mission called Cassini that actually went to the Saturnian system, and it did a lot of great measurements about Saturn, Titan, but also went to Enceladus, and it actually did a flyby. We discovered at that time that there was a plume, and it did a flyby through the plume with the instrument. So that was fascinating. So one of the debates, that was many years ago, more than a decade, the measurement. So we were wanting to know is that plume there, and how active. So we were trying to do the same measurement. We point the telescope, and we wanted to hoping to see a small signature near Enceladus. We have the big moon and then maybe a little dot nearby. But we didn't see that. We actually saw a huge plume. The plume, look at the Enceladus was a single pixel because it's very far, but the plume is much bigger. It was, at least 20 times bigger than the moon, and it was a huge jet that made a massive cloud. And it was so surprising that I couldn't believe it. Actually, it took me, no joke, it spent weeks looking at the data. I could not believe that the plume of water coming out of that. So this is the biggest source of water in the Saturnian system. It provides water to everything in the area. Actually, delivers water to Saturn, that little moon. And that water has been spewing for years. After Cassini, we discovered that the amount of water coming out from the plume is so huge, and it remains steady for at least for a decade or decades, has been that way. So that definitely is a window into the subsurface of this object. But the other fascinating thing about this also took us time to understand that, is that you can see that in here, there's like a donut, blue donut here shown. Well, that is not a graph. That's not a donut. It's what we call a torus of gas. So what happens? This moon is going around Saturn very quickly. Actually, a few days just goes around around Saturn. And that means that it's kind of flying around and releasing all that water. It kind of leaves a tail of water around. It's like building like a cloud of water around it, and that builds up and produces like a torus of water. So we not only saw the water coming out of the jet, but we also saw this huge cloud of water behind Enceladus coming from the torus. So this is a really fascinating object. Again, it's the main source of water in the full Saturnian system. And it tells us that this object definitely provides a window into the subsurface ocean. The challenge, we only saw water. We didn't see the other molecules. And actually, this plume is definitely 99% water. So we are trying to understand why the other molecules are not showing up. And we are actually making observations this summer to see, we're going to spend longer making measurements. We are integrated longer that allow us to sense more deep, to look for more tenuous gases, and see if we can actually detect the other molecules like methane. We're looking for CO2 and see if they're there. And again, back to the Europa debate, we want to be able to understand the chemical diversity in that place. So the Rhine hypothesis, and this is how we envision, or we like to envision Enceladus in the interior. We have an autothermal vent that is building the subsurface ocean. Then there are cracks connecting to the surface, and then those cracks are releasing that water. Then the water immediately gets frozen, and it produces these little particles of water ice. And finally, the water that we see with James Webb is not water ice. We were actually seeing water vapor. So we see gas. We actually saw gas coming out of Enceladus. And this is just to remind, this is very, 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 very far away. It's almost twice the distance to Jupiter. It's 9 times the distance to our own planet, the distance to the sun, our planet, we call astronomical unit. So it's very, very far. And you need a humongous telescope like James Webb pointing that way to actually make those measurements. So, well, I just wanted to show you that. And I think it's exciting. I have to say, as an astronomer, I've been waiting many years, I would say my life, for something like this happening. So I think you're going to be hearing a lot of new discoveries like that. And I think it's an enticing for new discoveries, for new exploration, to give us new possibilities to test for the possibility of life and habitability in our solar system.